Hello.
Good evening,
Audible.
sir.
In last class, I have just started to deducing relationship. Just revising you. Suppose if you have to calculate any of the given quantity, say Q, which has dependency on A, B, and C. So from this, you can make a formula or you can formulate this as Q proportional to A, B, C. And this particular proportionality may be directly or inversely and maybe of linear power or maybe some different exponential. That's why I have put X, Y, and Z related to its relationship. Now, if you remove this proportionality and put a constant, you will get Q is equals to K, A raised to the power X, B raised to Y, and C raised to Z. So this would be your expression to get the value of Q using dependency A, B, C. Now from this, write the dimension of Q. Similarly, dimension of A, B, C raised to X, Y, Z respectively. Now compare the exponent of each part. Means exponent of M on left hand side, exponent on M on right hand side, that should be equal. Similarly, exponent of L, similarly exponent of T as well. On comparing, you will get the value of X, Y, Z. Is it clear?
Yes, sir.
Just write it down. I'm giving one example.
Done, sir.
Vaishnav, done?
Yes, sir.
I'm giving you a problem. Suppose the time period of oscillation of simple pendulum depends upon first mass of bob and second length of string L, third acceleration due to gravity. Use proportionality constant K to be 2 pi. So how to define it? Suppose if you have a support and this is your reference point, string having length L connected by a metallic bob having mass M. So it will swing to and fro from one point to other like this. So it will have a fixed time period, let's say period of revolution or period of oscillation, which depends upon three factors: mass of probe, length of string, and acceleration to gravity. So from this, you can formulate T is equals to some proportionality constant K, dependency over M, L, G raised to X, Y, and Z. So this is how we can formulate according to the dependency of time on these three different quantities. Is it clear, Namuna?
Yes, sir.
Now we have to write dimension of each segment on left hand side and right hand side. So first we have time in left hand side. So its dimension would be M0, L0, T raised to 1. In right hand side, we have K, which is nothing but proportionality constant. So it would be dimensionless constant part. So we can neglect it. Next is mass raised to X. Next is length raised to Y. And next is gravity, means acceleration, LT minus 2 raised to Z. So it will be M raised to X, L raised to Y, L raised to Z, and T raised to minus Z. Now we have L raised to Y and L raised to Z, both having same base and in multiplication. So their exponent will be added. So you'll get M raised to X, L raised to Y plus Z, and T raised to minus of 2Z. Is it clear till this part?
Yes, sir.
Vaishnav, Abdul Wahid,
Explain it again, sir.
yes?
Can you
Is it-
explain it again?
Okay. I've just written dimension of T on left hand side. So it would be M0, L0, T raised to 1, as it has only dimension of time. Similarly, for right hand side, the first term is K, which is nothing but proportionality constant. So it will have nothing or unitless quantity. So we can neglect it. Next is mass to the power X. So it will be M raised to X, L raised to Y, G's acceleration due to gravity having dimension LT minus 2 raised to Y raised to Z. Z would multiply it with L as well as T. Now these two terms having same base, so their exponent would be added. So you will get M raised to X, L raised to Y plus Z, and T raised to minus 2Z. Is it clear now, Vaishnav?
Yes, sir.
Now you have to compare on comparing the exponent on each side. First, for the exponent of M, in right hand side, we have M raised to X, but in left hand side, we have M raised to 0. So on comparing, you would say X is equals to 0. Similarly, if you solve for L, we have L raised to the power Y plus Z in right hand side, but we have L raised to 0 in left hand side. So on comparing, you can say Y plus Z is equals to minus 1. Next is exponent of T, which is minus 2Z, but in left hand side, we have 1. So you can say minus of 2Z is equals to plus 1. So on moving minus 2 to the other side, you will get Z is equals to minus 1 by 2. So this is our first part, Z. Put this value Z in the second equation. So Y plus Z minus half is equals to 0. Or if you move this term to the other side, you will get y is equals to plus. So we have calculated value for x, y, and z. Is it clear, Namu, now?
Yes, sir.
Abdul Wahid, is it clear? Now you have to put term in each part in the above equation. You will get t is equals to k. K is nothing but 2 pi as given here. M raised to x, which is 0. L raised to y, which is plus half. And g raised to z, which is minus half. So it will become 2 pi. M raised to 0 is 1, so neglected. L raised to half and g raised to minus half. So on moving to denominator, it will become plus half. Now these two terms having same exponential, so we can take it together. So you will write it as 2 pi L over g whole raised to the power half. Half in exponential can be written as square root. So it will be written as 2 pi root of L by G is equals to T, that is time period. So this will be our final conclusion or final result for calculation of time period for simple pendulum. Is it clear, Vaishnav? Mamuna, do you have any doubt?
No, sir. It's clear.
Okay, just write it down.
Done, sir.
Wahid, Vaishnav, have you written?
Wait a minute, sir.
Okay.
Sir, finish.
Good. The time period of the revolution of a planet around the sun depends upon first mass of sun, second universal gravitational constant, capital G, and third distance from sun. Use K is equals to 2 pi, obtain the result as E square is equals to C times R cube. Then find C. So you have to find time period of oscillation, which depends upon three different parts: mass of sun, universal gravitational constant, and distance from the sun. So it would be T is equals to some proportionality constant K, m raised to x g raised to y and r raised to z. This will be your formula. Now put the dimension on each side, and on comparing, try to find the value for x, y, and z. Okay. Try to solve. Write the dimension of each part. Dimension formula of capital G is mn minus 1 t raised to minus 1 L cube t raised to minus 2. Shoaib, have we done? Namuna, any doubt while solving?
Where I found like t is equals to 2 pi r 3 by 2 divided by square root mg. But after that, I don't know how to get p square is equals to c r cube.
Just take squaring both sides.
Okay.
So on squaring, you will get t square is equals to 4 pi square divided by g times of m into r cube. Okay, Mamuna?
Yes, sir.
So just compare these two equations, this part and this part. So what should be the value for c? Vaishnav, have you done?
No, sir.
First of all, write the dimension on each side. We have t in left hand side, whose dimension would be m0, l0, t raised to 1. In right hand side, we have k, which is proportionality constant, so just neglect it. Next is m raised to x. Next is gravitational constant having dimension m minus 1, l cube, t raised to minus 2, and whole power y. R is length, so its exponential would be z. Now simplify it. So m raised to x, m raised to minus y, l raised to 3y, t raised to minus 2y, and l raised to z. On simplifying, you will get same base, so the exponent will add, so it will become m minus 1. For length, we have 3y here and z here, so it will be 3y plus z. And for time, we have minus 2. Is it clear till this part, Vaishnav? Abdul Wahid? Shab, is it clear? Now on comparing the exponent on each side. First, for the component or exponent of m, we have left hand side x minus 5 as exponent of m, and on right hand side we have 0. Similarly, 3y plus z is equals to 0 as exponent of L, and last is minus 2y is equals to 1 exponent of p. So from it, y would be equals to minus 1 by 2. Put this value in the second part, you will get 3 times y plus z is equals to 0. So it will be minus 3 by 2. Move it to the other side. So z would be equals to plus 3 by 2. Put this value of y in the second part. So x would be equals to y, and which would be equals to minus 1 by 2. Is it clear, Vaishnav? Shoaib, do you have any doubt till this part? Just write it down. Have you written? Abdul Wahid, have you written? Now put these values in this first equation. You will get t is equals to k, which is 2 pi, m raised to x, which is minus 1, g raised to y, which is minus 1, and r raised to z, which is 3 by 2. Take squaring both sides, so it will be t square is equals to 4 pi square m raised to minus 1, g raised to minus 1, and r raised to 3. This term containing negative exponential would move to denominator. So you will get 4 pi square divided by g times m times r cube is equals to t squared. So just compare this expression with this part. So what would be the value for C, Mamona? C would be equals to
T square divided by R cube.
where C is nothing but coefficient of R cube. So from this expression, what's the coefficient of R cube here?
4 pi square divided by GM.
Good. So C would be equals to 4 pi square over G times M. Is it clear, Shreyam? Vaishnav?
Yes, sir.
Okay, just write it down. Abdul Wahid, have you done? Vaishnav, have you written?
Yes, sir.
So this is how we derive or deduce relationship on the basis of dependency of different points. Now there is some limitation of this dimension analysis. Limitation of dimensional analysis. First limitation is in each of the previous problem, I have defined the proportionality constant k to be 2 pi, k to be 1 in all of different problems. It means using dimension analysis, you won't able to find proportionality constant for that particular expression. So dimension analysis is unable to define the value of proportionality constant. Next is, in all of the previous problem, I had just defined only three dependency, A, B, C, whether in terms of this part, I have given you just three terms. In previous part, I have just given you three terms. It means dimensional analysis is valid up to find relationship up to maximum of three terms. For beyond three terms, sometimes it will give you correct result, sometimes it will give you wrong result. So it will be better to find only maximum of three terms. So it is applicable to derive relationship between quantities up to maximum of three terms. Next, in equation, some of the formula would be in terms of multiplication or division, and some of the formula may be containing plus or minus sign as well. Suppose if you have s is equals to ut plus half at squared, v square is equals to u square plus 2as, pressure plus half rho v square, and so on. So in these type of equation, when quantity contain plus or minus sign are called composite relationship. With the help of dimension analysis, you won't be able to calculate these type of relationship. Using dimensionless analysis, you can only find relationship between quantities having product or division relation. So it is not applicable to derive relation containing plus or minus in between quantity. Is it clear? These limitations, Mamuna,
Yes, sir.
just write it down. Wahid, any doubt? Okay.
Sir,
Yes.
for example, if we have two quantities which have same dimensions, then we can add, right?
Yeah.
Okay.
According to principle of homogeneity, two quantity can be added, subtracted, or equated only if they contain same dimensions. Vaishnav, have you written?
No, sir. Just a minute. Finish, sir.
Okay. So we have just finished this dimension analysis. Next part in this chapter is error analysis, in which first topic is accuracy and precision. Do you have any idea about what we mean by accuracy and precision?
Accuracy means that it indicates how close the measured value is to the true value.
Good. And what about precision?
It indicates the resolution of the instrument.
Okay. Let's say if you have gravity, so it is 9.8 meter per second square. And if you do some experiment using simple pendulum to find this particular gravity, you may find it like 9.76 meter per second square, 9.81 meter per second square, 9.85 meter per second square. Vaishnav, tell me which of this experimental value is most closest to the actual value. First is 9.76, second is 9.81, third
The
is
second
9.
one, sir.
Good. So for any of the experimental value, the data which is most closer to the true value is called accuracy. So let's say this is your true value and this is experimental value. So accuracy simply defines you the closeness of experimental data with true value or actual data. Now, what we mean by precision? To define precision, you must need to define least count of a particular instrument. Mamuna, do you have any idea about it? What do you mean by least count? Sure. Vaishnav? Least count is nothing but the smallest value an instrument can measure is called least count. So you can say the smallest value an instrument can measure. We have different instruments for measuring different amount of length and so on. Suppose for meter scale, we have 0, 1, 2, 3, and so on. 0, 1, 2, 3. In any of the two consecutive number, there would be 10 division in between. 1, 2, 3, 4, 1, 2, 3, 4, and so on. So in this part, the smallest value which can be measured using this would be this part. And from 0 to 1 is in centimeter. And this smallest division is 1/10 of that particular centimeter. So we can call it as 1/10 centimeter, or it is equals to 1 mm. So this is the least count of meter scale. Similarly, there would be different value for vernier caliper, screw gauge, and so on. Depending upon least count, it will give you different value for the measurement of same quantity. Suppose if you measure the thickness of lead of a rifle or in thin wire by using meter scale, vernier caliper, screw gauge, it will define you different measurement. Let's say by using vernier caliper, it would be 1.5, 1.4. If you are calculating in terms of mm, it will be 1.51, 1.49, 1.48, and so on. But using screw gauge for the measurement of same thing, it will give you 1.496, 1.491, 1.495, and so on. So just see in this expression, these three data are closer within themselves, and these three data are closer within themselves. Is it clear?
Yes, sir.
So precision simply defines you the closeness of experimental data within themselves, and it would depend upon least count of that instrument. Smaller the value of least count, it will define you more precise data. So precision simply defines you the closeness of experimental value within themselves. So smaller the value of least count, it will give you more precise result. Is it clear, Vaishnav?
Yes, sir.
Just write it down.
Done, sir.
Abdul Wahid, have we done? Vaishnav,
Yes, sir.
have you written?
No, sir, just a minute.
Okay. Done, Vaishnav?
Yes, sir.
Okay. I'm giving you some example regarding it. Let's say if you have the central part is defining you the true value related to that measurement. On the basis of different observation, you have to define whether these data are precise or accurate. Accuracy and precision. Let's say first is this, second is this, third is this, and fourth is this. In first part, we have all data are closure within themselves. So we can say it is or it having high precision. So precision will be high. And since all data are more closer to the accurate one, that is central one, so it will have high accuracy. Is it clear? Similarly, try to define for this part whether the data are closure within themselves or not. Rational.
Yes, sir.
Are the data in this part are closure within themselves or not?
Nearly closer, sir.
So we can say it having high precision. But the distance of this experimental value from this accurate data is quite far. So we can say it having low accuracy. Is it clear, Namuna?
Yes, sir.
Tell me about the third part.
It has high precision.
Are the data closer within themselves?
No. So
So it
it has
having,
low. Yeah.
and what about accuracy? Are they closer to the accurate one?
Yes.
So it having high accuracy. Vaishnav, tell me the last part.
Sir, low accuracy, low precision, sir.
Good. So it will have low accuracy and low precision. Is it clear, Wahid, Shram? Just write it down.
Done, sir.
Yes, sir.
Have we done? Now the next part in this topic is to define significant figure and rounding off. Suppose if you have to measure length of a particular rod, let's say this part. So for this measurement, you need an imager scale. So you have put just side by this. Let's say like this. Having measurement starting from 0, 1, 2, 3, and so on. So they would have 10 division in between. Let's say 1, 2, 3, 4, 1, 2, 3, 4. So this will be your 0, 1, 2, 3, and so on. Depending upon observer to observer, this measured term someone will say this particular value from observing from one side from this side, they will define it as 2.3. Similarly, from the other side, it would be 2.2 from this way. So it will be 2.2 centimeter, and from this side, it will be 2.3 centimeter. So depending upon observers, this particular measured value would be different. Now in both these two values, the first part is 2, here it is also 2. And the next part, here it is 2, but here it is 3. So we can say the first part in any of the measurement or measured value, like in this part, is defined as true value. And the next or the last digit for that measurement would vary from observer to observer. So we can say it having some uncertainty, or it will be called as uncertain digit. So the total number of digit in true value plus one uncertain digit in any of the observation is called significant figure. Is it clear? What do you mean by significant figure?
Yes.
Namun, okay. So we can say the number of digits in true value plus one uncertain digit is called significant figure. Now we have certain rule to find number of significant figure in different calculation. So rules for finding number of significant figure. I'm defining you rules for decimal number only. First, all non-zero digits for any observation are significant. All non-zero digits are significant. Next, if 0 lies in between two non-zero digits, then it will be significant. If 0 lies in between two non-zero digits, then it will be significant. Suppose 0.502. So here 0 is lying in between two non-zero digits, so it will be significant here. Similarly, if 0 lies right two decimal and left two non-zero digit, then it is insignificant. 0.05. So in this part, 0 is lying right to decimal but left to non-zero, so it will be insignificant. So we have only 5 as significant in this part. Is it clear till this part?
Yes, sir.
Shrab, do you have any doubt? Vaishnav,
Yes, sir.
any doubt till this part?
No, sir.
Just write it down.
Done, sir.
Finish, sir.
Sure. Done. Okay. Now, next property or next rule is if 0 lies right to decimal and right to non-zero, then they are significant. Let's say 0.20. So this 0 is right of a decimal and right to non-zero digit, so it will be significant. Next, exponent is insignificant. If you convert a numerical value from one system to another system, its number of significant figures would remain same. While changing unit, number of significant figure will remain same. And last, for non-decimal number, if 0 lies right to non-zero digit, then they are insignificant. Just write it down and try to define number of significant figure in each. Write the number of significant figure. Just 1 minute.
Sir, finish.
If you just send your answer,
Sir, finish, sir.
try to solve this problem and send your answer. Amuna, just recheck it. Is this last rule? Number is non-decimal and total number of zero, right? Two non-zero digits are insignificant. So just remove all the zero. We have to calculate total number of significant figure in each part. Let's say for the first part, we have 0.50. So for any of the decimal number, if zero lies right to non-zero digit, so they are significant. Just use this concept. So we have two significant figures, and here we have exponential. Exponential is insignificant. So we can say it have only two significant figures. Okay, Mamuna?
Okay, sir.
Similarly, in second part, zero lies in between two non-zero digits. So all are significant. So we have three significant figures in it. Similarly, try to find for the rest of the part. Shab, have you solved? Just send me your answer. Vaishnav, have you solved?
Yes, sir.
Just send me your answer. Rest. Okay. Good, Momona. Shab, send your result. Vaishnav, just see in third part, we have this 0, which is right to decimal, but left to a non-zero digit. So it will be insignificant. So we have only 3 terms in this as significant. Okay.
Okay, sir.
In question number 4, since this number containing no decimal, so it can say it is a non-decimal digit. So all of 0 right to a non-zero digit are insignificant. So we can say it have only 2 significant figures, 6, 4. In last part, this 0 is right to decimal and left to non-zero, so it will be insignificant. But this 0 is right to decimal and right to non-zero digit, so it will be significant. So we have 2 significant figure in this. So it will have 2 significant figure, 2 significant figure, 2, 3, and 3. Is it clear, Shreya? Abdul Wahid, is it clear? Bashma, have we done?
Yes, sir.
Okay. Now we have 2 more rules regarding different operations. First, while adding or subtracting. Suppose if you have to add 4.32 to 1.5, you will get 2, 5 and 3 would be 8.5. So it would be 5.8. In any of the number, the total number of significant figure after decimal. In first part, we have two significant figures. In second part, we have one significant figure. It will define you precision related to that measurement. As we have discussed in last part about least count, smaller the value of least count, it will define you more number of digits after decimal. So it will define you more precise data. So you can say the more number of significant figure after decimal, the more precise data it will be. So we have from this part 4.32 most precise data and 1.5 least precise data. So according to the rule of significant figure, while adding and subtracting, the result of this operation should be reported in least precise data related to input. So according to the rule, while adding or subtracting, the result should be reported in least precise data related to input. So in this part, we have 1.5 having only one significant figure after decimal. So we can say this is least precise and this is most precise. So in your final answer, there would be only one significant figure after decimal. So we have to round off this particular number to one significant figure after decimal. So in this part, we have 2, which is less than 5. So just neglect it. So your answer would be just 5.8. Is it clear, Mamuna?
Yes, sir.
Similarly, if you have to multiply or divide, suppose 4.32 into 1.5, 15 into 2, 30, 15, 3, 45, plus 3, 48, and 15, 4, 60, plus 4, 64. We have one place here and two place here, so it will be 6.480 in total. Now, the total number of significant figure as a whole for any of the observation will define you its accuracy. So you can say the more number of significant figure as whole, the more accurate data it will be. So from this, you can say this is more accurate data and this is lesser accurate data. So according to the rule of significant figure, it simply tells you while multiplying or dividing, the answer of this operation should be reported in least accurate data related to input. While multiplying or dividing, the result should be reported in least accurate data related to input. So Mamuna, which one is the least accurate data in these two observations or these two input? Vaishnav, in
Yes, sir.
4.32 and 1.5, which is least accurate?
1.5, sir.
How many significant figures are there?
2 significant figures, sir.
So the result should contain only 2 significant figures.
Only 2 significant.
That's why we have to round off this particular number for 2 significant figures. So what would be your result for this rounding off? What you will get on rounding off? We have to keep it just 2 significant figures. So we have to round off this particular number. So what you will get? 6.5 or it will be 6.4.
6.5.
Vaishnav, whether it would be 6.5 or 6.4. Share. There is one rule of rounding off. Suppose the data which you have to round it off, if it is even and the next number is also even and the next is even. So even can't round off to an even number if the next data after it is also even. Since in this part, 4 is even and 6 as well. So we can't round it off. So your final answer for this particular would be just 6.4. Is it clear? Namuna, is it clear?
Yes, sir.
Even can't round it off even number, but there would be all possibility rest of it. Odd can round it off odd, even, odd, even, so on. But only for even, it can't be possible. Is it clear, Sharon? You just write it down, this whole part.
Done, sir.
Finish, sir.
Sure, done. Abdul Wahid. Okay. Now, on the basis of this, the next part is to define about error. theory of error. So first of all, what do you mean by error? Suppose for the value of gravity, let's say 9.8 as its true value. And while experimenting, you will get some experimental data. The difference in this experimental data with respect to its true value is called error. Okay, so error is nothing but the deviation or difference of experimental data with true value. It's called error. We may have two different types of error. First is called systematic, and second is called random error. Systematic error is mainly inbuilt with that instrument and we can't get rid of it. Suppose if you have to measure length of an object by using any metallic ruler, and if you done this experiment first in summer season and second in winter season, depending upon surrounding temperature, the length of a metallic rod or metallic scale would differ. So in summer, you will get some different value, and in winter, for the measurement of same object, you will get different value. These two measurements would depend upon surrounding factor, temperature, and so on. These type of error are called systematic error. Is it clear?
Yes, sir.
Next is random error, which arises due to human mistake while taking observation, while observing the data, and so on. So it can be minimized by increasing number of repetition. The more the number of repetition you are taking for the same experiment, the random error will get reduced. So it will get reduced by increasing number of repetitions. So we can say random error is inversely proportional to number of repetitions. Is it clear, Rashna?
Yes, sir.
Okay, just write it down. Chef, do you have any doubt? Abdul Wahid, any doubt? Okay.
Sir, finish, sir.
Good. Now, Mona, have we done?
Yes.
Shab, have we written? Okay. Now, on the basis of this random error, I'm giving you some experimental value. Let's say for any observation, x1, x2, and so on to xn are some experimental value. So first of all, if we take mean of these experimental data, it will be x1 plus x2 plus so on to xn divided by number of data is called mean value, average value, or we can call it as true value. We may write it as summation xi divided by number. This particular term is called true value. Now, from this true value, just take the deviation of each experimental data with respect to true value. So we have to take deviation. Let's take delta x1. So it should be equals to x1 minus x bar. And since this difference would sometime give you positive value and sometime would give you negative value, but if you have to take only positive part. That's why I have put modulus or absolute value here. So you have to take only positive value. Similarly, delta x2 would be equals to x2 minus x bar mod and so on, delta xn minus x bar and mod. Now, if you take the mean of this whole data, delta x bar, it will define you delta x1, delta x2, and so on to delta xn, whole divided by number of data n, or you may write it as summation delta xi divided by n. This is called absolute mean error. Is it clear till this part? Mamona, is it
Yes.
clear? Okay. So we have just calculated true value and absolute mean error. Using this, you may write your answer in result as true value plus minus absolute mean error. So it would be x bar plus minus delta x bar, or you may remove bar, so you will get x plus minus delta x as your final answer. Now from these two values, absolute mean error and true value, I have to define two more terms. First is called fractional or relative error. It would be represented by delta, and it is equals to nothing but absolute mean error divided by true value. So it will be delta x divided by x. Now, if you multiply it by 100, you will get percentage error. So percentage error or delta percent is equals to delta x divided by x into 100. Is it clear till this part to everyone? Vaishnav?
Yes, sir.
Okay, just write it down. I'm giving you an example regarding it.
Done, sir.
Okay. Rational, are we done?
Yes, sir.
Abdul Wahid, okay. Just use this concept and try to find the time period of simple pendulum is 92 seconds, 95 seconds, 93 seconds, 94 seconds, and 93 seconds. Find first true value, absolute mean error, fractional and percentage error. Try to solve using the same formula which we have discussed in last part. All of you just send me your first answer about true value. Namuna, have you solved the first part?
Yes, sir. I'm sending.
Shrab, just send me the first part. Vaishnav, have you done?
No, sir.
Just see how to solve for this true value. We have 5 different observations. So for taking true value, you have to take mean of all. Mean is nothing but sum of all observation divided by number of observation. So T bar is equals to 92, 95, 93, 94, 93, and whole divided by number of data 5. Just sum up this all and divide by 100, divide by 5. You will get true value. Try to simplify it. Good, Namuna. But you have done a little mistake. If you solve this, you will get 4, 6, 7 divided by 5. 2 plus 5, 7 plus 3, 10 plus 4, 14 plus 3, 17, 7. 9 into 5, 45 plus 1, 46. So it will be 467 divided by 5. On dividing by 5, 5 in 9 times, 45, 1, 7. 5 in 3 times, 15. Point 5 into 4. So this should be your answer for true value. Now, just see in this part, we have three significant figure in this, but in our observation, we have only two significant figure. So first of all, you have to round it off this particular data up to two place decimal. So it will be 93 seconds. Now you have to take deviation of each data with respect to its true value. Let's say delta T1. So it should be equals to 92 minus 93 mod. 92 minus 93 minus 1, but for modulus term, it will give you just plus 1. Similarly, delta 2, 95 minus 93, it will be 2. Delta 3, delta T3, 93 minus 93, 0. Delta T4, 94 minus 93, 1. And delta T5, 93 minus 93, 0. So if we take its mean, 1 plus 2 plus 1 plus 0 plus 0, whole divided by 5. It will be 1 plus 2, 3 plus 1, 4 by 5. It's 0.8. So according to this, you can write your result for time is equals to true value, that is 93, plus minus the error part, 0.8 seconds. Is it clear, Namuna?
Yes, sir.
Yes, sir.
Rashma? Okay. Shwab, any doubt till this part? Good. So if you have to take fractional error, it is nothing but a ratio of error part divided by its true value. Similarly, if you want to calculate percentage error, it would be 0.8 divided by 93. So it will be around 0.86. So it will be around 0.0086%. Just write it down. Abdul Wahid, any doubt? Good.
So now, sir, if I did not do that rounding of significant figures, right? So I wouldn't get marks for the fractional error, percentage error, right?
It will be slightly different from the actual value. So you will have to first round it off this particular true value according to the data. Okay.
Okay, sir.
Have you all written?
Yes, sir.
Vaishnav, done?
Yes, sir.
Abdul Wahid, Shab, done? So do you have any doubt from today's class to any one of you? Namuna, any doubt?
No, sir. No.
Okay, so just revise this whole part and try to do more and more problems regarding it. In next class and onward, I will define you how to operate different error, whether in addition, subtraction, multiplication, and exponential, and then we'll start mathematical portion for this physics. And after completing it, we will start third chapter, that is motion straight line. Okay?
Okay, sir.
Okay then.
Thank you, sir.
Thank you.